Hello future pilots, we are going to start the first chapter of instrumentation, which is pitot and static sources. So before we start the chapter, I'm going to teach you about what is static pressure and dynamic pressure. So let's read this. An aircraft at rest on the ground in still air is subject to normal atmospheric pressure, which bears equally on all parts of the aircraft. This ambient pressure is known as static pressure. So what this sentence is saying is that when the aircraft is on the ground and is in still air means the air molecules are on the aircraft is still and it's not moving. That means the aircraft is subjected to normal atmospheric pressure. So the air molecules around the aircrafts exerts pressure on the aircraft, which this pressure which is exerted is called the static pressure and is equal on all the parts of the aircraft. This ambient pressure is known as static pressure. Alright, now we're going to study about dynamic pressure. So let's read this again. An aircraft in flight, while still subject to the static pressure at its flight level, experiences an additional pressure on the leading edges due to the resistance of the air to the aircraft's movement. So let me explain you what is dynamic pressure. So when the aircraft is in flight or even if it is moving, so obviously there will be air molecules in front of the aircraft. That air molecules hits the leading edges of the aircraft, and this the pressure which is exerted on the leading edges of the aircraft is what we call as the dynamic pressure. But you have to keep this in mind that even if the dynamic pressure is exerted, the static pressure also exists, just like when you see the picture over here. Okay. So here it is written that dynamic pressure value depends on the speed of the aircraft and density of the air. So let's see how. So it is very obvious that when we increase the airspeed of the aircraft, it will cause more molecules to hit the leading edges of the aircraft, and which will cause an increase in the dynamic pressure. Similarly, when the density of the air also increases, more air molecules will hit the leading edge of the aircraft and will cause an increase in dynamic pressure. So here it is written that more the speed and density, more pressure on leading edges, more the dynamic pressure. Okay. So we have to understand the next topic, which is that what is pitot pressure or total pressure. So pitot pressure or total pressure is nothing, it's just that static pressure plus dynamic pressure is pitot pressure. Alright. And in the note it is written that only dynamic pressure cannot be calculated. So when we see the both scenes in the above picture, like when the aircraft is on the ground and also when the aircraft is on the flight, we can see that only dynamic pressure doesn't exist. It always exists with static pressure. So the only way to isolate the dynamic pressure is to by this method. So to calculate dynamic pressure, we have to minus pitot static pressure from pitot pressure or the total pressure. Alright. So next we are going to study about the Aviation Six Pack. So this six instruments you should have a basic idea before starting the next chapters of the instrumentation. So what is an airspeed indicator? From the name itself, you can say that airspeed indicators indicates the airspeed of the aircraft, which is the speed of the aircraft. And next is the attitude indicator. So what is attitude indicator is that attitude indicator indicates the attitude of the aircraft, like when the aircraft's nose is up or the nose is down. So this yellow line you can see, right? So when the nose is up, it shows more of the blue and less of the ground, and when the nose is down it shows more of the brown or ground and less of the blue, right? And it also shows us the bank angle of the aircraft. Next is altimeter. We know that altimeter indicates the altitude of the aircraft or the height of the aircraft above any specified point. Next is turn coordinator. Turn coordinator says us the rate of turn, and also shows us that if the aircraft is skids or is slipping, right? Heading indicator indicates the heading of the aircraft. Vertical speed indicator shows us that how much at what rate the aircraft is climbing or descending. So why I teach you this is there's a reason behind it, is that airspeed indicator works on dynamic pressure. Okay, but as you guys know that dynamic pressure only doesn't exist. We have already studied about this, right? Only dynamic pressure cannot be calculated. So I will write here that total pressure or pitot pressure minus static pressure, which gives us dynamic pressure. Okay, all right. Next is altimeter. Altimeter works on static pressure. All right. Next is I'm going to say about is that vertical speed indicator. So vertical speed indicator also works on static pressure. And now in the next videos I will explain you how these instruments work. But for now you have to learn this, that static pressure is used in altimeter and vertical speed indicator, and pitot and static is used in airspeed indicator or Mach meter. All right. So next we are going to study about how are static and pitot pressure sensed. Inside an aircraft, pressure and temperature are rarely the same as outside the aircraft. So pitot and static pressure must be sensed by devices mounted on the outside of the aircraft. So what this statement says is that inside an aircraft, the pressure and temperature differs from the pressure and temperature outside the aircraft, right? So to sense correct pressures, we have to put devices on outside of the aircraft, right? So what are the devices? These devices are pitot heads and static heads. So let's start with pitot head. So this is how a pitot head looks like. So if you see the in front of the pitot head, you can see a hole. So let's read this. The open end of the tube faces into the moving airstream, means that this hole, yeah, or this pitot device is facing the moving airstream, which is that means that it is parallel to the airflow, right? And from the name itself, we can say that pitot head senses the pitot pressure, which is the static plus dynamic pressure. So here it is also written that this sensing dynamic plus static pressure, right? Next, we are going to study about static heads. So, we know by the definition of static heads, static pressure, that it has to be in a still condition, still air. We want the still air, we don't want the moving air. So, this hole or this slot does not face into the airflow like the pitot head. It is perpendicular to the airflow and thus only senses the static pressure. Alright. So the next is the static and pitot sources may be combined in one pressure head. So as we can see from this picture, from here the pitot pressure is sensed, and from here the static slots, from the static slots the static pressure is sensed, right? Requirements of a pitot tube. The pitot tube must be positioned outside the boundary layer. So it usually consists of a head on a strut if mounted on the side of the fuselage, or it can be a tube placed on the nose ahead of the fuselage. The opening must be designed to be parallel to the airflow in the normal flight attitude. So let me explain this. The first line says that it should be positioned outside the boundary layer. So what is this boundary layer? So it means that it wants to be positioned in the undisturbed airflow, meaning that the airflow which is unaffected by the presence of the aircraft. From this example, we can see that this airflow is unaffected by the presence of the ship, or we can just say it as the aircraft, right? So this requirement of the pitot tube says that it should be positioned outside the boundary layer. That is the reason, if you see, it is also written that it can be a tube placed on the nose ahead of the fuselage, because if we keep the pitot tube on the nose of the aircraft, so it will only receive the unaffected airflow, right? And next important thing that you have to understand that is that it is designed to be parallel to the airflow. Why? What is the reason behind that pitot tube is parallel to the airflow? Because pitot tube, the reason is that it wants to sense the dynamic pressure, and to sense the dynamic pressure it has to face the moving airstream, so it is parallel to the airflow. So let's read what's written in this note. The air can either be brought to rest in the pitot probe against a stagnation wall, which is simply a pressure measuring flat surface, and then transmitted up to the pitot pipelines to the ASI and Mach meter. Alternatively, the pitot pressure can be passed directly up into the pitot pipelines to the instruments, which is more usual in elementary aircraft. So it actually, in this note it is written that there is two ways by which the instruments work by the use of pitot tube, right? So there might be a stagnation wall on the pitot tube, which is a pressure sensing wall, which senses the pressure and then transmits it to the pitot pipelines to the ASI and manoeuvre. And there's another system which is more common in elementary aircraft, which passes the pressure directly to the pitot pipelines to the instrument. So there's no stagnation wall or there's no pressure measuring flat surface, right? Next we can see is measurement of dynamic pressure is essential to flight safety, right, or the safe flight. At low speed the aircraft will stall. At too high speed it will be overstressed. So these are the reasons that why dynamic pressure is so important for us to sense properly, because if the airspeed of the aircraft is too low, then it will stall, and if the aircraft's airspeed is too much high, it will be overstressed, and which will cause damage to the aircraft. The ASI is critical. ASI is the airspeed indicator, is critical to flight safety, and so it cannot be allowed to block because of ice. So as you can see, this pitot tube, if this pitot tube only gets blocked, then the ASI won't work, and we know that how much essential it is for a safe flight, right? So there's a heater in the pitot head that causes the ice. If there's any ice formation on the pitot tube, then it melts because of this heater. And there's also a drain hole which which drains the excess water. Next we're gonna study about is the requirements of a static source. The static source, whether a simple hole or a combined probe, should have its opening at right angles to the airflow, so that only static pressure is sensed with no component of dynamic pressure. Some static sensors, especially those in the combined pitot-static probe, may be fitted with electrical heating. So let me explain you the requirements of a static source. So the main requirement of the static source is that it should be right angles to the airflow, and that means that it should be perpendicular to the airflow. But let me explain you why it shouldn't be parallel to the airflow, because if it is parallel to the airflow, it will also sense the dynamic pressure, right? So to sense only the static pressure and no component of dynamic pressure, it is perpendicular to the airflow. And especially those in the combined pitot-static probe, from this image you can see it is also fitted with electrical heating. So next we're going to study about is position error. So if the aircraft has forward motion, the static pressure sense will be slightly lower than if the aircraft is stationary due to suction. As the speed increases due to turbulent airflow in the region of the pitot-static heads, this error becomes greater. Turbulence will also affect the pitot reading. This error involved is called position error, or alternatively pressure error. So let me explain you by this diagram. So an ideal airflow is supposed to be looking like this, right? So from here pitot pressure is sensed, and from here static pressure is sensed. But the airflow is not ideal, right? So it is a typical airflow looks like this, that when the aircraft moves, the air becomes turbulent. And here in the statement it is written that the static pressure sense will be slightly lower than if the aircraft is stationary due to suction. Now let me explain that what is suction. What causes this suction? So the airflow above this pitot tube is way more faster, and from the Bernoulli's theorem we have know that if the velocity is more, the pressure is less. So if the pressure is less, the comparatively the pressure inside the slots of the static slots is more. So there's a pressure difference creating, and thus causing an like we know that pressure moves from high to low, right? Everything moves from high to low. So the air molecules also gets carried away uh, by the higher velocity airflow, right? Position error depends mainly on the positioning of the pressure head, the airspeed, and the aircraft's attitude. So let me explain you how position error depends on the positioning of the pressure head. So we have already studied in the requirements of pitot head and static head that it is placed in the parallel to the airflow, or it should be in the perpendicular to the airflow. So by that understanding, we can you can understand that how much important it is to position on the right place to sense the correct pressure. Then it is written that it also depends on the airspeed. So if the airspeed changes around the static slots, it causes changes in the pressure differential, right? And which causes more error or less error. So it depends. The position error also depends on the airspeed. And lastly, the aircraft's attitude. So when aircraft's attitude is changed, right, if it is the angle of attack is changed or it is banged, so it causes turbulence around the static slots, which causes more position error. Okay. Next is turbulence produced in the airstream by the pressure head itself affects the value of the static pressure. So because of this structure, the airflow which was flowing like this, because of the structure it becomes turbulent, and which itself affects the value of static pressure. All right. So because of position error, the static vent was introduced as a source of static pressure instead of the static head. So I will explain you how static vent is different and better as compared to static head. So static vent looks like this. Okay, you can see from this picture also and this picture also. It looks similar. So in this plate, a similar vent is positioned on the opposite side of the fuselage, and the two are interconnected for transmission of static pressure to the instrument so that errors produced by yawing are largely eliminated. So the difference is that static vent is placed on both sides of the fuselage so that when the aircraft yaws to the left, for example, so the static pressure which will be sensed on the left side of the static vent will be different, but the right static vent will sense more accurate pressure. So this is the reason both side of the fuselage will have static vent, and this is how it is more advantageous for having a static vent rather than a static head. So here it is, the advantages are also written. The airflow in the regions of vents is less turbulent and the static pressure measured is more accurate, right? So from above explanation also you can see that it was written that due to the structure of the pitot head, right, due to the structure of the pitot head, it affects the value of static pressure, right? So but why this structure, you can see that the turbulence will be less as compared to the static head, right? Errors produced while side slipping or yawing are reduced. Duplication of static vents either side of the fuselage reduces errors due to slide slip or yawing. I have already explained you this. Next is high speed probes. The shock waves associated with flights at high Mach numbers can produce significant errors in pressure sensed by a static vent. Modern high-speed aircrafts may accordingly be fitted with a more sophisticated combined pitot-static pressure head in order to keep position error within acceptable limits. The choice of location for a probe or vent is dependent upon the aerodynamics of the aircraft. So, the static vents that we just studied is also not sufficient for aircrafts which flies at a higher Mach numbers, because shock waves are associated with it and it can cause significant errors in pressure sensed by a static vent. So this is the reason high speed probes are introduced. Okay. Next we so next important topic is maneuver-induced error. Maneuver-induced error are caused by short-term fluctuation of pressure at the static vents and delays in the associated pipelines transmitting pressure changes to the instrument. So let me explain you what is maneuver-induced error. So near the static vents, if there is fluctuation of pressure which causes a delay in transmitting pressure changes to the instrument, this error is called maneuver-induced error. So let me explain you the causes of it. So when there is a change in angle of attack or the turbulence which is created by lowering or raising flaps and landing gears are the prime causes of error producing changes in airflow over the static vents, right? So when there is a change in angle of attack, the airflow around the static vents changes. When the flaps or landing gears are deployed, right? So there's again changes in the airflow and which causes a turbulence near the static vents and causes fluctuations of pressure, right? And this fluctuation of pressure is what we call this maneuver induced error. Most commonly, maneuver-induced error appears as a marked lag in pressure instrument. The errors are usually more significant during changes of pitch attitude than during yawing or rolling movements, so that the worst effects are at the start of the climb or descent and on leveling out. So let me explain you with an example. So when this aircraft is climbed, the VSI, which is the vertical speed indicator, shows 500 feet per minute. Okay, so but when the aircraft has already reached its altitude and has leveled out, so the VSI should show that the VSI should show 0 feet per minute because it is not climbing. But still, there's a delay in the VSI. The VSI still shows 500 feet per minute. And after some time, after this delay, some time, VSI shows 0 finally, right? So this marked lag is happens in maneuver induced error. Okay, next we let's read this pressure instruments cannot be relied upon to indicate accurate instantaneous rates of change, right? The higher the altitude, the longer the error will last. Why it is written that when the altitude is higher, the longer the prolonged the error will last? Because at higher altitude the air is less dense, right? As we go up, the air is less dense, so the pressure changes are also very low. The rate of change of pressure also decreases as we climb, right? And this causes longer for the static pressure to stabilize, and this prolongs the error. So let's study the full pitot and static system. So this white pipelines, if you can see, this is the pitot system, and this blue one is the static system. So this one is the captain's air data instruments, and this one is the first officer data instrument. All right. So although the captain and the first officer systems are independent of each other, as you can see, still they each sense from both left and right of the aircraft. This is very important for you guys to know, right? So next if you see this, there's here written is emergency static source. So when do we use this emergency static source? When there's a blockage on the main static source, right? Static vents, but due to icing or any insects blocked, right? So alternate static vent is used at that time. So it is not in the optimum location as compared to the actual static vent, right? So it has more errors. But where is it positioned? So in pressurized aircraft, it is positioned in fuselage, and in non-pressurized aircraft, it is positioned within the cabin. So let's read this one. The transmission from the probes to the instrument usually takes the form of pipelines in elementary and older system. But in modern aircrafts, it is usually carried by electrical wires. So in older aircrafts, what happens is the transmission of this pressure, no, it is directly uh, transmitted to the instruments by the pipelines, but in modern aircraft it is carried by electrical wires. Modern aircraft transmit the information electronically via pressure transducers at the pitot and static source. So on the last page of the notes, I have written all the summary of this lesson. And to get these notes, you can check the bio. I have already put a link over there. You can click the link and you can get these notes. Okay. So this is the end of the chapter, and thank you for watching.